This is going to be the lab titled Introduction to Magnets, and I've got everything set up for you, and we're going to walk through this, and some of this is pretty self-evident, but I want you to really see the magnetic fields. That's the true goal of this lab. So we're going to do it as a demonstration, and I'd like you guys to write in all the same material and submit it online, and you're going to be graded for that. So let's go ahead and begin. So we have two magnets here, and we discussed this in the lecture. What's going to happen? We have a north pole interaction. So north pole interaction. Of course, the magnets are not going to be attracted to each other. They have a repulsive effect. Their magnetic fields do not line up. So therefore, we have repulsion. So the interaction with north pole, this is going to be repulsive or repulsion. So, of course, south pole. South pole is also going to be the same effect. We're going to have repulsion because of that. The magnetic field lines are not going to line up, so we have repulsion. So why does that line up like this? We have north pole, south pole. We actually have attraction. So what I'm going to do is I'm going to bring in the next portion of the lab. It's already set up for us. What I want you to see first of all is the magnets. They're all aligned north to south, north to south, north to south, because a compass is actually a miniature magnet. So they're all in alignment. So what's going to happen if I bring in the magnet? We've got these 7 places, and we're going to draw the red as being the north. Okay, so what's going to happen when I bring in this magnet towards these other magnets? And that's the effect that we get. Okay, here's the south, here's the north. The north is being attracted to the south. Here's the north, the south is being attracted to the north. The magnetic field lines are going around like this in that circle. So if we can go ahead and try to draw this on your notes, I'll try to put it side by side so we can do this kind of together. Let's go ahead and get that there, that there. This looks pretty much like what we have. So draw the north in the arrow that it's going. So it's going to be going like this, like that, and so on. These are going to be pointing towards the south. And that's what it would look like. So I'm going to bring in the next part, and we're going to have drawing the permanent lines of the magnetic field. So here's a permanent magnet that we have. It doesn't really matter which is north and which is south. What I'm going to do is I'm going to cover this magnet with a card, and then I'm going to sprinkle some iron on top of it. So you can kind of see this magnetic field. Okay. So you can see the magnetic field lines, how they curve around this magnet. They all emanate and explode at the ends this way. They explode at the ends this way. And all these lines are the magnetic field lines, and they're all connected. So that's something I'd like you to draw on your lab, which is a representation of this. So these are the magnetic field lines, kind of emanating out like this. They emanate outward like this. And then you see these curves like this as well. And then these would go up like this. And these lines would eventually connect like that. These lines would eventually come around and and connect as well. So it's going to look something like that. So what happens when I bring in a north-south, north-south? I'm going to do the same scenario. I'm going to separate them with a little bit of space. We're going to see what this magnetic field looks like. There we go. What you can see again is there are curved magnetic field lines right here. But what you can also see is you can see the connected field lines between the north and the south. So rather than just exploding out into space like this over here, they're actually connecting with the magnetic field lines of the other magnet over here. So this is what I'd like you to draw over on the other side. So they sort of explode out over there. We can imagine they would probably explode out over there. Well, they're exploding out in both directions here, but they're actually connecting. They're making that bridge. That's the magnetic attraction. Then we have all these curved magnetic field lines as well, going around like this. So getting the next one, what would happen if you have magnets that are opposing like this? We have this repulsion. So here's the repulsiveness, here's the attraction, here's the repulsion. So what's it going to look like in between with those magnets? So you can see the magnetic field lines going around each of them, those magnetic field lines connecting. But look what's happening in here. We get absolutely nothing. No magnetic field lines are crossing. That's because we have this repulsive effect, and we have those same types of magnetic field lines that are not going to align with each other, and they're going to be having that repulsive effect. So if you can draw something that looks like this, we have the explosion coming out from this end. We have the explosion coming out from this end. We have our curved magnetic field lines going like this. Each has their own magnetic field. But then right here, as these lines come out, they are not going to align with each other. So it looks something like this. And that's the repulsion, because they're not being attracted towards each other. Let's go ahead and answer some of these questions. Describe what happens when two identical poles of the bar magnet face each other. What happens when two opposite poles face each other? After each of these questions, I'd like you to pause it and try to answer it on your own. And then hit play, and then you'll be able to continue. So two identical poles, what happens when two opposite poles face each other? We get a repulsion. And why do we do that? Because the magnetic field lines they do not connect with each other. They do not connect. What polarity must the red tip of the compass needle be since it points toward the south pole of the magnet? Red tip of the compass needle since it points towards the south pole of the magnet. Well, let's take a look at this. Here's the magnet, Here's the North Pole being attracted towards the South Pole. So when I release this, okay, just like the giant magnet, north is about right here in this direction. Okay, so why did it stop there? Again, it's being aligned towards the North Pole. Well, if it's being aligned towards the North Pole, that means the red tip is actually going to be what? Of the compass. So if you can pause and then come back. The red tip is actually the South Pole of the magnet. That means the North Pole of the magnet actually aligns towards the South Pole, if that makes sense. I hope that makes sense. The red tip is the South Pole of the magnet and points to the North Pole. What would happen if a bar magnet were cut into two equal pieces? We did this from lecture. Do you remember this? Pause, please, and then come back. If you take your magnet with the north and the south and we cut it or break it into two, all the electrons are oriented in the same direction. So you would create two new magnets. Like this. How does the direction of the compass needle change as the compass is moved along the magnetic field lines? Okay, so here's the south, here's the north, being attracted to the south. So we're going to move the compass. So going this direction, it moves clockwise around. So the north will be attracted to the south will be attracted to the north. How are iron filings lining themselves in relation to the magnetic field? Do the magnetic field lines ever cross? So, just like the electric field lines, those magnetic field lines do not cross. So the magnetic iron filings, they actually will become mini magnets. They will orient themselves to the magnetic field. The filings, each one becomes a miniature magnet, become magnets, and align to the magnetic field. And lines never cross. Never. Where is the magnetic field the strongest? How can you tell? This is also from lecture. Please pause and answer the question. Magnetic field lines are, magnetic field is going to be strongest where they're closer together. How can you tell? That's where most of the iron is. So magnetic field's the strongest. Strongest is where the most iron is. Compare the strength of the magnetic field to the closeness of the magnetic field lines in that region. Close lines equals a strong field. And the last question, is a typical refrigerator door made of iron or aluminum? Explain. Unfortunately, ours at home is made out of aluminum. And we have to tape everything to the front door. How do we know? Of course, the refrigerator magnets don't stick to them. I hope this is the correct spelling. The refrigerator, and I think it is a refrigerator. The refrigerator does not stick to magnets. Of course, if it is an iron door or a steel door, the refrigerator does stick to magnets, or the magnets do stick to the refrigerator. Okay, please go ahead and submit that when you're done.